It's just, well, 95 out of 150 is not that great.
I thought we were talking percentage.
I was, but I changed the, yeah, sorry, it's my way. Dear Heavenly Father, we thank you for this day again. I thank you for this class and just ask you to bless our work today. Help us to understand a little bit more about your creation together, Lord. In your name I pray, Lord Jesus. Amen. All right, so let's get into it. So today we are talking about the potential formulation of electromagnetism. And so let me begin with actually the definition. And then I will justify why this definition is a reasonable one. But I'm going to put the first thing, like basically here's the deal. Definition, given electric fields E and B, functions of position and time, we say V comma A is a set of potentials for E and B provided that B is the curl of A. Well, nothing new there, right? Seen, been there, done that, right? But this one's new. The electric field is minus the gradient of V minus partial A partial T. Now that's new. That we have not seen before. Now the question is, can we do this, right? And so basically here's the initial theorem. Given B is the curl of A, the field E plus partial A partial T is equal to minus the gradient of some scalar function V for some V. All right. And here I'm assuming, of course, that the electric and magnetic fields satisfy Maxwell's equations. That's the context in which I'm stating this theorem. All right? So the problem, as Griffiths explains, is, why can't we just still set E is equal to the curl? Why can't we say E is equal to minus the gradient of V now? Well, the thing is, we know that the curl of E is what? Faraday's law, right? So minus partial B partial T, right? And that's not equal to 0, generally speaking. So I can't just say E is minus the gradient of V. That's the problem. However, check this out. The curl of E plus partial A partial T, how's that work out? Well, it's the curl of E, all right, plus partial T of the curl of A. Here I've commuted the gradient and the time derivative as we always do in here, right? And that's great because this now is partial B partial T, right? So we've got curl of E plus partial B partial T, but that is also known as 0. So this vector field is conservative. So we can set E plus partial A partial T equal to minus the gradient of some voltage function V by our theory of vector calculus, because we have that the curl of this is 0. And the reason for the minus is the same as the usual reason, right? Notice that this set of potentials, it reduces to what we've talked about before from the magnetostatic or the electrostatic case, right? In the electrostatic case, the vector potential, well, in the magnetostatic case, there was no time dependence to the vector potential, right? So like partial A, partial T was gone. That was gone. And so like this reduces to what we've done before, but it also plays nicely with Faraday's law, right? That's the thing. Okay, so what? What's that? It is not unique. Far from it, and we'll talk about that. So here's the theorem. Given, a voltage and a vector potential, and as we were just talking about, B is the curl of A, and the electric field is minus the gradient of the voltage minus the time derivative of the vector potential, right? Then guess what? There's no magnetic monopoles, and Faraday's law holds. All right? But furthermore, I guess it's not really trash, but it's just not worthy. It's not worthy. If we have Gauss's law, the divergence of the electric field is rho over epsilon naught, and we have, the curl of the magnetic field is mu naught J plus mu naught epsilon naught partial E partial T. In other words, Ampere's law with Maxwell's corrections, then V and A must solve the Laplacian of the voltage plus the time derivative of the divergence of the vector potential is equal to minus 1 over epsilon, the charge density, and also the Laplacian of the vector potential minus mu naught epsilon naught partial squared A partial T squared minus the gradient of the divergence of the vector potential plus mu naught epsilon naught. Great, googly moogly, partial V partial T, close parentheses, equals to minus mu naught J. Well, that's a lot, right? So just if you're keeping track, if you're keeping score, this is Griffith's 10.4. And this is Griffith's 10.5 in terms of equations. All right. So let us prove this theorem. All right. So some of this is like stupidly easy, right? Like, how about the no magnetic monopoles? The divergence of B is equal to the divergence of the curl of A, but that's 0. We're done. I like that one. I've called the last couple of things past missions and past the surprise attack missions in differential equations this semester boss fights. I've got like boss fight 1 and boss fight 2. I was talking to my son on the way to school today. He said I should always make my tests. All my tests should be called boss fights. And it occurs to me, why am I not doing this?
This is a great idea. That was a boss fight.
I'm not, I've given my last test. From now on, only boss fights.
And you have the final boss.
That's right. And then the final is the final boss fight. That's right, yes.
I sure to myself because it was in the previously.
And then, of course, I need to add music, obviously. But, all right, so the Faraday's law, curl of E, right? It's almost the calculation I have right over here in the red, right? So the curl of E is the curl of minus the gradient of the voltage, right? Minus partial A partial T. All right. So curl of the gradient be 0. And so we've just got minus, and I'm going to pull the partial T out, minus partial T of the curl of the vector potential. Aha! But that is the magnetic field. So we have minus partial B partial T, and we're done. There's Faraday's law. So no magnetic monopoles and Faraday's law both follow immediately from our current potential formulation. What about the inhomogeneous equations, right? The ones with sources. All right, so great. We have that the divergence of the electric field is minus rho over epsilon, right? So that says that the divergence of minus the gradient of the voltage minus partial A partial T, right, is equal to minus rho over epsilon naught, which says that minus the Laplacian squared of the voltage minus partial T of the divergence of A is equal to minus rho over epsilon. Great, so like one more move. Why do I have a minus on Gauss's law? What's wrong with me? Good grief, man. Goodness gracious. Plus. Yeah. All right, there. Yay. That was this guy, Griffith's 10.4. And then what do we have left? We have, this guy, right? So next, I'll do in blue, I guess. The curl of B, which was curl of A, right, is equal to mu naught J plus mu naught epsilon naught partial E. Oh, but the E is what? Let me replace the E with what it is. Partial T of what was E? Minus the gradient of V, right? Minus partial A partial T, if I remember right. Let me check on that. Yeah. All right, but we know the deal. We've used this identity so many times that we now remember it. This is the gradient of the divergence of A minus the Laplacian of A. And that's equal to mu naught J minus mu naught epsilon naught, the divergence, how did I write it over here? Oh, gradient, yeah, gradient, pull the gradient out, we'll pull the partial V partial T inside, trying to make it look like that, and then here, and then that gives me, this is that term, right? But then also, so there's that's from this term. And then I also have minus mu naught epsilon naught partial squared A partial T squared. All right. Almost there. There's not too much, there's a lot of writing here, but there's not a lot of thinking, right? A lot of writing, not too much thinking. So, lo and behold, this brings us to nabla squared A, all right, minus mu naught epsilon naught partial squared A partial T squared minus the gradient of the divergence of A plus mu naught epsilon naught partial V partial T, close parentheses, equal to minus mu naught J. And there you go. That is the other equation which the potentials must solve. These two boxed equations I've just written are the implication of Gauss's law and Ampere's law with Maxwell's correction for the potentials. These are the equations we must solve. So, yeah. Kind of scary, huh? A little bit scary. So we could talk about gauge freedom. And you can show that if we put A prime equal to A plus the gradient of lambda, and you put V prime equal to V minus the time derivative of that same scalar function of space-time, this right here, so here, basically here's the theorem. If, V, A, give, your electric field E and B, then so do V prime and A prime. In other words, like to be explicit, I'm saying that B is equal to the curl of A, but it's also equal to the curl of A prime. And I'm saying that E is equal to minus the gradient of V minus partial A partial T. But guess what? That's also equal to minus the gradient of V prime minus partial A prime partial T. And I'm saying more than just that. I'm actually saying that that's the extent of the ambiguity. And this is derived in Griffiths, and I could drive it here. It wouldn't take us too long, but I don't think I'm going to belabor that point. Let me talk through it. So basically the point here is that if you look at the difference of A prime and A, its curl is 0, right? So like the curl of A prime minus A is equal to 0. So that suggests that, A prime is equal to like A plus the gradient of some function. And then when you study this equality here, it suggests that they can the vector, the V part of it can differ by at most like a time derivative of that function. Let's see here, I can.
So cool, gauge just to learn some electrostatics.
Oh yes, so okay, great. Fine, I'm feeling guilty for not talking about this. The gradient of V prime minus V is what? See, that's from here, right? These two are equal by assumption. We're assuming that we have two different potentials that generate the same fields. So that means this is equal to that, which means that the gradient of the difference of V prime and V is minus the partial T of what? A minus A prime, I think. Or A prime minus A. I put a minus there, right? I don't know. I'm going to get the signs wrong. I got a minus here. I think it's okay. But that's what? A prime minus A, remember, we've already argued is there's supposed to be a prime here. The gradient of lambda. And so then that suggests that if we look at the gradient of V prime minus V, plus partial lambda partial t, well then that's equal to 0, right? So then that tells us that v prime is equal to v minus partial lambda partial t, possibly plus a constant, right? But you could just absorb that constant into your definition of lambda. And that brings us to the boxed equations as the most general set of what are called gauge transformations. These are gauge transformations. Now Sam was saying something about the Coulomb gauge, right? So definition, Coulomb gauge is when we set the divergence of the vector potential to be 0, right? And I had an evil test question about this, right? You remember that one? Problem 1. That one, yeah, there was some trouble there. Yeah. I mean, I'm, come on, guys. If I derive something in class, that means you've memorized it forever. So, right? Sorry. I need to redefine my yeah, well.
I just fell short. That's all.
It's okay. It's okay. I think if you look at what you missed, you didn't miss much, really. It's actually a very simple mathematics. It's just a matter of identifying what you're looking at as a problem you've already solved and making a substitution. It's really just that. It's not deep. It really isn't. So, and then this is the Lorentz. Although more recently he's taking to calling it Lorentz gauge, because it's actually due to this guy, not that guy, but everyone spells it this way, so take for that what you will. So I think this is going to be one of those, like, how do you spell L'Hopital's rule kind of deals. Depends on which, thing you look at. The hospital rule, yeah. Anyway, it's actually the Bernoulli rule, so we're all wrong. Bernoulli has too many. I don't know, I think Bernoulli's don't get enough credit.
That's not fair. There's 4 of them.
Exactly. They should get there's 4. So that's the Lorentz gauge. And they each have their own place, right? Like if we go back and look at, all right, so let's look at this then. So equation, so here's, 10.4, right? Equation 10.4, Ella Griffiths, and this is 10.5. So I'll write it here. Lorentz gauge, my bad, Coulomb. So actually, let me erase the gauge freedom business now. We're done with that, so. All right. I'm sorry, what?
They're both, one's equal to 0 and the other's equal to the other thing. So,
well, I'm not saying that those are both equal to 0. I'm saying that they're equal to each other. Like I'm saying the divergence of A is minus mu naught epsilon naught partial V partial T. That's the Lorentz gauge.
Yeah, that would be 0, right?
That would be 0. Oh, I'm not enforcing. We can't enforce both.
Oh, okay. I thought they were both.
No. These are different worlds.
Gotcha. Okay.
It's like you can like Star Trek or you can like Star Wars, but you can't like both. No, I need to come up with better examples. But I need to come up with better examples. Let's see here. It's like should rip something from the headlines. No, I'll probably get everything in the headlines is gonna be fired. Let's see here. Maybe not. We have freedom of speech, right? Right until you say something, and then you're reminded that you work for a private company, and there is no expectation of freedom of speech, actually, in any kind of real practice of your existence. So it's kind of a funny thing. We have freedom of speech, just not where we work. So, yeah.
You're free to lose your job.
You're free to lose your job, yeah.
Can't lose what I don't have.
Okay, so if we have the divergence of A is equal to 0, then we've just got nabla squared V is minus rho over epsilon naught, right? And we know how to solve this. The solution is V of R comma T actually is 1 over 4 pi epsilon naught. The integral of rho of R prime T divided by d script R d top prime, right? That was the solution. And this is, as Griffiths points out, really, really disturbing in some sense, because notice rho is function of time t now, right? So I'm saying that the voltage changes, right, at some point over on Alpha Centauri as a result of the charge changing here with no time delay. So that's a little bit disturbing, right? Because it's like the time here and the time here are coincident, and there's no time, there's no like delay. There's no delay for this changing, making that change, right? And so here we have the source points, here we have the field points. There's no delay between source and field point. But
It's not retarded.
yeah, this is not retarded yet. Don't worry, we're going to get retarded. We're going to get really retarded. Give me a minute. So, actually being retarded is really, really smart in this section, as it figures. But, okay, so here's the deal. We don't measure the voltage directly, though. What do we measure? We measure electric fields, right? And the electric field is minus the gradient of the voltage minus partial A partial T, right? And that partial A partial T, this guy has to solve that, which is slightly simplified. Ooh, this is 0. Yay, what a simplification. Not really, though, right? So calculating A in the Coulomb gauge is monstrous if the sources are time varying. So you don't want to do this, is what I'm telling you. And for that reason, from here on out, we will adopt the Lorentz gauge. Now, the Lorentz gauge is very nice. It's very, very nice. In fact, because what does it make 0? Yeah, that whole thing in the parentheses, right? So if we have that, the divergence, oh man, this marker's trash. All right, let's try this again. So we're given that the divergence of A is equal to, you know, minus mu naught epsilon naught partial V partial T, right? So that means that this equation becomes nabla squared A minus mu naught epsilon naught partial squared, come on, partial squared A partial T squared, gone, equals to minus mu naught J. Well, that's much improved. Hooray. Right? In the Lorentz gauge. But what about the other one? Let's see here. So this equation, right? How can we, what's the divergence of A equal to? Minus, see, it becomes, oh, look at that. It becomes nabla squared V, right? Minus mu naught epsilon naught, partial squared V, partial T squared, equal to minus rho over epsilon, minus 1 over, minus 1 over epsilon naught rho. That's do you guys, do you track what I'm doing? What I'm doing is I'm replacing this divergence of A, right? I'm replacing that with this business. And when I do that, I've got a time derivative of a time derivative, which gives me a double time derivative. And I pick up this constant, which I pulled out. So like, just to color code for a second, in the Lorentz gauge, this term becomes this term. That's all that happened. But this is very nice because we can rewrite both of these in terms of the box squared. This is box squared A equals to minus mu naught J. And this is box squared V equals to minus 1 over epsilon rho. That's, in fact, in the Lorentz gauge, of course. And I just feel like it is, I'm sorry, I got to put the T on that. I cannot stop writing the T there. I'm sorry, I know it's improper, disrespecting the history of the matter, but the T belongs. So, in Lorentz gauge. And here, box, oh, come on. Box squared is Laplacian minus mu naught epsilon naught partial squared partial T squared. This right here is called the D'Alembertian. The D'Alembertian, which is essentially the four-dimensional, what's wrong? I think they can't, what happened? Something happened? What? I'm confused.
I thought the camera was pointed at like the wall.
Oh. Okay, well, thank you for your concern. Much appreciated. All right, so great. Now, all right, lovely. So that is, so the equations I just boxed over there, those are, I think Griffiths calls them inhomogeneous wave equations. It's kind of what they are. They're essentially the four-dimensional Laplacian, though, is what they are. So this gets even more beautiful as we study special relativity at the end of the course, all right? But okay, so then the question is, how do we solve these things, right? How do we solve these equations? All right? Same, what do you say? Same way, but four dimensions in a different metric? Maybe, but what I'm about to write down is completely three-dimensional. Well, okay, fine, 3 plus time. So I guess it's always space-time, isn't it? But so basically the remainder of chapter 10 is devoted to understanding how to solve these equations. Not just that. So first of all, how to solve these equations, which I'm going to write down the solution for you, and hopefully we'll show it works in the time that remains. And then past that, the next section's on Jeff-Menko's equations, which I forget how to explain quickly. And then finally, at the end of the chapter, we have actually the formulas for the electric and magnetic fields due to a moving point charge. So the current consideration is not for a point, these aren't point charges, it's for like continuous distributions. That's the current business, is we're trying to solve Maxwell's equations in the potential formulation with possibly time-varying sources, right? And also possibly a continuous distribution. And so for that, we introduce the retarded potential. And the idea for this it's so stupid. I mean, I don't know. But basically, we introduced the retarded time. T sub r is equal to T minus script r over C. So here, script r, as per usual, is the distance between the field point and the source point. All right? And so the idea here is that time is the time at which the field point would get information about the source point. You know, it's tracking back in time, the time before the time you're at. If there was a signal moving at light speed from, you know, the source point, then that would get to the field point. Right. All right. So anyway, so the solution then that's proposed is we simply write the voltage at position r and position time is obtained in the usual way, except we replace time with retarded time. So these are exactly the potentials, formulas for the potentials we wrote, you know, previously in electrostatics and also magnetostatics in the case of, you know, static sources. But we're doing the same thing, but we're just replacing time with retarded time. And there's, I mean, this is the reasoning being that if we believe in special relativity, that, you know, things travel at the speed of light and no faster, then this would take into account for the travel time from the source to the field point. Now that does not prove that these work, right? That's just kind of a heuristic justification. Griffiths points out that, in fact, if you tried the same trick with the, you know, we have those formulas for calculating the electric field or the magnetic field from basically Coulomb's law or the Biot-Savart law in terms of the integrals over the densities. If you just retard those, if you make those formulas retarded, they don't work. Actually, the field equations, if you try to like directly modify the Coulomb formula or the Biot-Savart formula, they don't work in this way. It has to be done at the level of potentials. So the claim is this. These solve, you know, number one, the Lorentz gauge condition. This I will not show in class. Not today anyway. It's a homework problem. I wonder if I assigned it. It looks pretty, looks like a pretty feisty problem. I don't know. So number one, these are in fact, they play nice with the Lorentz gauge condition. These are actually Lorentz gauge compatible. And number two, they solve the inhomogeneous wave equations. And I will show you just half of part 2 in class if I do my job. All right? No. This does not imply those. The Lorentz gauge condition simply simplifies equation 10.5 and 10.4. Well, 10.4 it complicates a bit, I suppose, but I don't know. It's kind of the same, kind of a wash for 10.4. But the Lorentz gauge condition for Griffith's 10.4 and 10.5 equations, it puts them in this symmetrical form. But that is a separate issue from solving those equations. All right, so let me get to it. This is the point at which I wish I had scanned my notes. All right, so we're just going to look at this. We're going to try for this. All right, we're going to aim for this. Here we go. So, nabla v would be 1 over 4 pi epsilon naught times the integral of the gradient of 1 over r times rho d tau prime. But that would be 1 over 4 pi epsilon naught is the integral of the gradient of 1 over r times rho plus 1 over r times the gradient of rho d tau prime. So I'm doing the old product rule right there, right? But now I must confess to you that this I'm going to put the step right here, but then I'm going to explain it next. Okay. This gradient of 1 over r is simply minus 1. So I get like minus 1 over r squared, and that's r hat, if you will, from this term, right? And then the other term, 1 over r, as it happens, that works out to minus 1 over c rho dot r hat. Let me elaborate on the reason for the minus 1 over c. And that rho dot just means the derivative of the density. All right, so like technically speaking, everything here is like a function of r prime and the retarded time, I guess. Let's see if I can write this out. So I think this piece is not this is not mysterious. This is just stuff we've done before, right? But this piece over here is a little bit more mysterious. And so the logic for that is this. We're taking the gradient of rho, which is like the gradient of technically rho of r prime and the retarded time, right? But by the chain rule, that's just partial rho partial tr times the gradient of the retarded time. And my logic for that is that we're taking the gradient with respect to the field position, right? And the source position and the field position are independent. So as I think about, I mean, this is a function of 4 variables. So in principle, the gradient would involve 4 different kinds of partial derivatives. But this is all I'm left with because of the independence of the field and the source point. And then this is, so this, I denote that by just rho dot. All right, that's rho dot. And then what was TR? Oh, here it is. Right? So that gives me minus 1 over c and the gradient of script r. But the gradient of script r, we worked this out before, is simply r hat. And that's why we put that there. So far, so good, yes? No? Maybe so? All right, let me continue. I must make myself some space. I guess I'll do it over here. I'm going to regret erasing something here, I'm sure of it. I was going to write those equations 10.4 and 10.5 like out on the side somewhere, so I wouldn't be stuck working around them. But as you can see, poor planning on my part. What's that? I know, but I just can't. I can't bring myself to work over there. A window. Work on the window. All right. So. Let us continue on here. So we have that if we look at the Laplacian of v, which is of course the divergence of the gradient of v, right? That is actually, pull the 1 over 4 pi epsilon naught out, right? And then we've got the integral of the divergence of, I'm going to pull the minus out as well in that formula we had over there. So minus the divergence of rho over r squared plus rho dot over RC, and that's all in the rho hat direction, d tau prime. All right. Oh man, I was going to erase that. I'm a victim of my own failure to erase. So, let me get to the next. I'm not sure this even makes... That's not what I wanted to... Well, son of a gun. Oh, no, this is okay. The offending spot I haven't gotten to yet. So, yay. I'll skip it. Like, I knew I had an error line here, but I forgot to cross it out because I was in a hurry. My bad. But anyway, so this gives us the divergence of, goodness gracious, rho times r hat over r squared, right? This first term, plus the, oh, come on. Oh, I'm just missing it. I'm sorry, my stupid, I've forgotten to write a dot there and it's bothering me. All right, fine. Rho dot over C, r hat over r. All right. Then, all right, I have minus 1 over 4 pi epsilon naught, the integral of, all right, so I have gradient of rho dot r hat over r squared plus rho times the gradient of r hat over r squared. So I'm using the product rule here, guys. And then plus 1 over c, the gradient of rho dot r hat over r, plus rho dot over c, the divergence of r hat over r, d tau prime. But I'm going to save myself a little bit of writing here. This right here, we already know what that is. We worked that out before. That one works out to minus rho dot over c r hat. So r hat, right? That's this term. And this right here is rho dot over c, and this is actually minus rho hat over r squared, right? Like the divergence of r hat over r is actually minus rho hat over rho squared. My point is just that this term and this term cancel. They're the same, but with minus. Now, this one here, by an argument similar to the one I already made, I've got minus 1 over 4 pi epsilon naught, the integral of rho times the divergence of rho hat, not rho, but script r, impossible to tech r over impossible to tech r squared. And this gives me a minus 1 over c squared rho double dot over rho r hat dot r hat over r. So like basically the same calculation I did for rho, I can do for rho dot. Like when we differentiate this, it pulls down a minus 1 over c again, and it pulls out an r hat. Like it's the same calculation that we did for the gradient of rho. All right, so I'm almost done with this calculation here. So what we got is all right. Phew. Minus 1 over 4 pi epsilon naught, the integral of rho, and by the way, the divergence of this is 4 pi three-dimensional delta of script r vector, yay. And to be fussy, that's actually rho of what? Well, I'm just going to leave it as rho, fine. All right. And this right here, I have minus 1 over c squared rho double dot oh. There's no, I've got an extra R there somehow. I don't know where that came from, guys. That's just supposed to have a 1 R, not 2 on the rho double dot term. I think it's because I've forgotten what the identity was. Oh, yeah, look. There's no division by R in this, right? It just is minus rho dot over C, so we get minus double dot over C. The R that's there is just the R that was there to start with. This thing right here does not give me another R. It just gives me, the R that was already here stays, and this just gives me, you know, the R rho double dot R hat. And then I get this, I got the 1 over, I get the C here, and there's the C that was there before. So I get 1 over C squared, R double dot, rho double dot rather, over, good. Rho double dot, script R, man, I hate this symbol, over R, d tau prime. But this is a Kronecker delta. So we've just got minus rho of RT divided by epsilon naught, by the way. And this we can rewrite as, you know, plus 1 over C squared times the second time derivative of 1 over 4 pi epsilon naught, the integral of rho of r prime tr divided by script r d tau prime, which is also known as v of rt which is to say that, what does that say? Yeah, it says that nabla squared v minus 1 over c squared partial t squared v is equal to minus rho over epsilon naught. In other words, box squared v is equal to minus rho over epsilon naught, which is exactly what we set out to prove here. Eh? I mean, wow, just it's so cool. Now you can actually, so I'll start next class probably with an example. I'll probably project it, but right there, right after he does this derivation, he shows you that he derives the electric field and the magnetic field for a wire, infinite straight wire that carries current, which like turns on at time 0 and starts flowing, and like you're able to actually see the electric and magnetic fields non-zero in a growing like cylinder of influence as the current flows, right? Like at the start, if you're more than, you know, the speed of light away from where the current's flowing, you don't you know, like CT, the influence spreads as like the wave, you know, the speed of light away from where the source is changing. It's very cool. We'll look at that in our next class. Now, all I have else today to tell you is that there is something rather perverse here, that if you study the mathematics that we just did, there's nothing really stopping us from going back to the start, and instead of putting a minus there, you notice that you could have just as well put a plus. And then you'd have A for advanced time, the advanced time potentials. So the effect of the current flowing would be going back in time. So we don't think these are physically reasonable solutions, since time goes forward, not backwards, but there is what's called time reversal symmetry here. The solutions to the inhomogeneous wave equations both allow for forward time and backwards time solutions. So,
How do we know time is going forward?
well, I've never been able to go backwards. That's all I can tell you.